All right, I'm going to see if I can use these Newton's laws to some successful end here. So this is numbers 1 through 11 odd from chapter 5. Only two horizontal forces act on a 3 kilogram body. That can move over a frictionless floor. One force is 9 newtons acting due east, and the other is 8 newtons acting 62 degrees north of west. All right, so what do I have here? I've got one acting due east with a magnitude of 9 newtons, and the other one is 62 degrees north of west. And that has a magnitude of 8. Okay? What's the magnitude of the body's acceleration? All right, well, I need to know the sum of the forces. So let's see, I need to break this one into its I and J components. So this one's all I. We call that force 1 is equal to 9I newtons, and force 2 is equal to, make sure that I am in degree mode, I am. So let's see, 8 cosine of 62 is 3.8, and that is in the negative direction. Got to be super careful about your signs. The J component is going to be positive. That's going to be 8 times the sine of 62. That's about 7.1. So the sum of these forces is 5.2I plus 7.1J. And let's see, so the magnitude of that, which I can write like this, you can use absolute value signs to do the magnitude. The magnitude of the sum of the forces is, got to Pythagorize those, the square root of 5.2 squared plus 7.1 squared, which is about 8.8. That's the magnitude of it. I could find the direction by doing tangent inverse, but I don't think that I need to. They just want the magnitude of the acceleration. So I can now use Newton's second law. And I don't have the vector hats on these, which is an indication that I'm only dealing with the magnitudes of them. So 8.8 is equal to 3 times the acceleration. So the acceleration is about 2.9. That's the magnitude. What's the direction? Well, it's whatever the direction of this is. Remember, the sum of all forces and the acceleration must have the same direction. But they didn't ask me to do that, so I'm not gonna. Number 3, if the 1 kilogram standard body has an acceleration of 2 meters per second squared at 20 degrees to the positive direction of an x-axis. All right, let me just get that stuff down. I got a 1 kilogram mass. It has an acceleration of 2 meters per second squared. And the acceleration is in the direction (20 degrees) above a positive x-axis. What's the x component and the y component of the net force acting on the body, and what is the net force in unit vector notation? All right, so I think I can find the acceleration in unit vector notation. So let's say that this is my acceleration vector. I'd like to find the components of it. So let's see, I got 2 times the cosine of 20 is about 1.88. That's the x component of the acceleration, and the y component of the acceleration is 2 times the sine of 20, 0.68. All right. And what do they want? They want to know what's the x component and the y component of the net force. Well, the force in the x direction is equal to mass times the acceleration in the x direction. And the force in the y direction is equal to the mass times the acceleration in the y direction. So, and the mass is just 1, so it's just 1 times these things. So that means this must be 1.88 newtons, and this must be 0.68 newtons. I think that's A and B, isn't it? Yep. What's the net force in unit vector notation? Well, it's the sum of these. That seems like kind of a silly question after we just did that. It's 1.88 I plus 0.68 J newtons. That's it. Number 5. Let's see. Hold on 1 second. Just going to check those 2 answers so far and make sure I haven't led you astray. 2.9, that looks good, and all good there. Okay. So number 5, 3 astronauts, you got a little picture there, propelled by jetpacks, push and guide a 120 kilogram asteroid toward a processing dock, exerting forces shown. They give you some angles and directions and stuff. What's the asteroid's acceleration in unit vector notation, and magnitude and direction relative to the positive x-axis? All right, so what do we have here? I have 3 forces. F2 is just all right here, and that has a magnitude of 55 newtons. That's F2. And then F1 at 30 degrees is 32 newtons. And then down here, F3 is 41. All right, and we want to add those up, so let's do that. So here, F1 is going to be both positive components. 32 times the cosine of 30 is 27.7 I plus 16J. I know some things about special angles. And force 2 is all I and no J. And F3 is going to be 20.5 I, that's half of that, plus, actually minus, right, because the y component or the j component will be negative. 41 times the sine of 60 is 35.5. So the sum of these forces is, what is it? Is it 103.2? Oh dear, I'm flying by the seat of my pants here. I think that that's right. Oh, let's just check. 27 points, and not worth making the mistake. Trying to be a no calculator hero. That was right. And then minus 19.5. Okay, so let's see. What do they want? How do they want us to report the answer here? What's the asteroid's acceleration in unit vector notation? So if the sum of all forces is equal to mass times acceleration, then acceleration is equal to the sum of all forces divided by the mass. So for parts A and B, I just need to divide these by the mass of the asteroid, which is called the masteroid. Just kidding, that's not really a thing, but you could smash those words together, kind of asking for it. 120 kilograms it is. So I just need to divide those. 103.2 divided by 120.86 meters per second squared. That's the I component. And then negative 19.5 divided by 120 is about negative 0.16 meters per second squared in the J direction. And part C, how about the direction relative to the positive x-axis? So, the direction of the net force and the acceleration are the same, so you can tangent invertize these or these. You're going to get the same thing. The ratio, of course, this is just adjusted by a factor of 120, so the ratio will be exactly the same. So tangent inverse of 19.5 over 120, not putting the negative sign in there, that gives me 9.2 degrees, and I have positive negative, so that's like quadrant 4, or you could say below the positive x-axis. And let's just do a quick check of those to make sure we're good. Yep. Oh, my angle's a little off. Why do they have negative 11? Huh. They also have an extra answer. Oh, they wanted the magnitude. So if you Pythagorize these, I guess part C actually is to do that. What's the magnitude and then the direction? What did I do there? Oh, I divided by, oh, I see what I did. I just divided by the wrong thing there in my tangent inverse expression, 103.2. Yeah, there it is. It's 11 degrees, not that. So, sorry about that. All right, number 7. There are two forces on the 2 kilogram box in the overhead view. A little picture there, but only one is shown. Okay, that's weird. Whatever. So there's my little XY axis system, and then here is force 1 in the positive direction of the x-axis, and it has a magnitude of 20 newtons. And the acceleration, the magnitude of it is 12 meters per second squared. And theta, here it's 30 degrees. I think that I'm more interested in angles that are measured. Actually, I don't think. I know I'm always more interested in angles that are measured from the horizontal. So the acceleration is, that's the 12 meters per second squared. Okay. I'm going to find the magnitude in unit vector notation, and then as a magnitude and angle relative to the positive x-axis of the other force. So just kind of thinking about where that other force would have to be, there's going to have to be enough of it to cancel this out, right? And then some more in that direction, right, to get it this way, and then some down. So let's see if we can figure out how to do that. I know that the sum of all forces is equal to mass times acceleration. Right? So I've got F1, and then I've got some F2 that I don't know. So this is all in the I direction, and then this I don't know. But I do know that the acceleration is 12 meters per second squared, and that the mass is 2 kilograms. So the sum of all forces, the magnitude of it, is equal to what did I say, 2? Is it 24? Sorry, I spaced out there for a second. The acceleration is 12 and the mass is 2. Yeah, 24 newtons. And I don't know that, oh, I do know the angle because that's got to be that's at 60 degrees below the negative x-axis, because the acceleration and the net force, the sum of all forces, have to be in the same direction. So I think I actually know what the answer here has to be, don't I? I know that the sum of all forces has to be equal to, well, it's 24 newtons, and the x component, that would be 24 cosine 60. Oh dear, I'm embarrassed that I just did that with a calculator. And that's in the negative direction. That's negative 12i. And then the j component is 24 times the sine of 60. It's about 20.8 j newtons. So what I'm looking for is, what do these things have to be? Well, it looks like F2 would have to be negative 32i, right? So that when I add those together, I get negative 12. And this would have to be 20.8, because there was nothing to add it to there. So then the whole 20.8 must come from this. And I think that those are the answers for, or that's the answer for A. Negative 32 plus 20.8. And magnitude and angle relative to the positive direction of the x-axis. So the magnitude is going to be 32 squared plus 20.8 squared. That's part A right there. Part B, looks like the magnitude's about 38.2 newtons. And when I do the tangent inverse of rise over run, that gives me 33 degrees. That's negative positive, so that's above the negative x-axis. Can you see that over there? All right, check that answer real quick. Let's see how we did. Number 7. Yeah, they called the angle negative 147 degrees, but that's the same as that. Oh, wait, negative 147? Because I have negative positive. Oh, that should be negative 2, shouldn't it? Because, yeah, sorry, that's the third quadrant, so this should be negative. My bad. And then that's 33 degrees below. Oops, there we go, fixed. All right, number 9 is we got a 0.34 kilogram particle moving in an xy plane according to, all right, so I've got, these are called parametric equations, right? I've got the x and the y given separately. We've seen things like this before, little vector functions. Not any problem for us. this, if you're thinking, oh, this smells like calculus, if that was your first thought, that's what it smells like to me. Nothing like the smell of calculus in the morning. With x and y in meters and t in seconds at time 0.7 seconds, what are the magnitude and angle relative to the positive direction of the x-axis, the net force, and the direction of travel? Okay, so, well, what's the direction of the net force is the same as the direction of the acceleration, right? Since Newton's second law, whatever the direction of the acceleration, that must also be the direction of the net force. So let's go ahead and find that. So velocities, the calculus you have to do in physics class sure is easy, huh? And then the acceleration, so that. Okay, so at time 0.7, there's those, and would like to know the magnitude and angle of the net force. Okay, so force equals mass times acceleration. So the components of the net force are these accelerations times the mass. So times 0.34. And the y direction of course you could just write this the whole time. You could say, oh, that the force at time 0.7 is equal to 5.7 newtons I direction. Sorry, I usually put the newtons at the end. I should be consistent. And sometimes I get excited about writing I's and they come out looking like J's. And then sometimes I should wait and put a minus, and I just put a plus there. Yikes. All right, how's that? 5.7 I minus 6.12 J newtons. So there it is in unit vector notation. But what do they want? They want the angle and magnitude and angle. So magnitude here is going to be 5.7 squared plus 6.12 squared. Is going to be the magnitude of that is about 8.4, and let's see, got positive, negative, so that's down in the fourth quadrant. Tangent inverse, rise over run, about 47 degrees. Fourth quadrant, so that is below positive x-axis. And see, how about the direction of travel? Well, the direction something's going in is the same as the direction of its velocity. So I would need to know what is the velocity at time 0.7. It looks like the x component is going to be 2 minus 12 times 0.7 squared. It's negative 3.88 I. And then the y component, 7 minus 18 times 0.7. is negative 5.6 J meters per second. So the direction of travel is the direction of the velocity. That's in the third quadrant. Tangent inverse 5.6 over 3.88. That is 55.3 degrees below the negative x axis. Let's check those real quick. See how we did. Chapter 5, number 8.27, that's good. They have negative 133 degrees, that's good, that's the same, and then negative 125, yep. All good. B, they have, except for B, they have negative 133 degrees. Is that the same as this? Below the positive x-axis. That is not the same as that. Did I make a sign mistake somewhere? Oh, maybe I did. Yeah, I lost a negative sign there, didn't I? So that is going to change that, and it is going to make this, now it's negative negative, so that's below the negative x-axis. All right, fixed. Little mistakes, little mistakes. If you feel like your physics teacher shouldn't be making little mistakes like that, well, I don't know what to tell you. I'm just a human. And the tests, assessments are certainly designed so that small mistakes like that are not going to be massively expensive. I mean, you don't want to make too many of them. Number 11, a 2 kilogram particle moves along an x-axis being propelled by a variable force, and its position is given by, we have, this is just one-dimensional here, so I just have x, only horizontal position, plus 4t plus ct squared minus 2t cubed. I got that right. And the factor c, that's some constant. At time 3, the force on the particle has a magnitude of 36 in the negative direction. So the force at time 3 is negative 36. And they want us to find C. All right, that should be easy enough. So if I have position and want to get to force, I need to get through to acceleration, and then I can connect up to this. So the velocity would be the derivative of this, 4 plus 2ct minus 6t squared. The acceleration would be 2c minus 12t. And the mass of this thing is 2 kilograms. This particle, it's a big particle. And so let's see, that means mass times acceleration. Well, you could find the acceleration at time 3. That's going to be 2c minus 36. And the force at time 3 is equal to the mass times the acceleration at time 3. So the mass 2 times this, that's equal to 4c minus 72. And they told us that that's equal to negative 36. So I got 4c is equal to positive 36. So c equals 9, looks like. Let's just check that, see how we did. And yep, and they put units on it. The units of that constant would have to be, if this is coming out to be meters and you're multiplying by a time squared, it would have to be meters per second squared. So there you have it. There's that assignment. Under 30 minutes. But the dominoes thing, if I took 5 more seconds to do this, you'd have to get it for free. I have to give it to you for free. Oh,